All right, so this is the video that's intended to help you with the review sheet that I'm giving you to work on in class Monday while I'm out. So this sheet right here is what we're talking about. The first page of this sheet is all notes and just knowing things that were in the notes. So let's take a look at what it is you're supposed to know. First of all, the types of elements that are involved in ionic and covalent bonding. When you're looking at ionic bonding, it's always a metal and a nonmetal. The only thing that metals can do to make compounds anyways is ionic bonding. Nonmetals, on the other hand, have choices. If there's no metal around for a nonmetal to bond with, it can bond with another nonmetal. It can bond with a metalloid. It can literally bond with itself. Whenever nonmetals bond with other nonmetals or metalloids, they produce covalent bonding. In ionic bonding, we had substances with low ionization energy and low electron affinity bonding with other elements that have high ionization energy and high electron affinity. Metals and nonmetals. The metals had low, the nonmetals had high. Because of that, you had elements that were willing to lose electrons and those that were willing to take them. Metals, because of their low ionization energy and electron affinity, are the ones that are willing to lose them. Nonmetals, because of their high ionization energy and high electron affinity, are the elements that are willing to take them. When you start combining two nonmetals together, or a nonmetal and a metalloid, both elements involved will have high ionization energy, high electron affinity, so they can't transfer the electrons. Both elements want to gain, neither element wants to give. Because of that, they have to share their electrons to satisfy the octet rule. The sharing of electrons results in the formation of molecules. In ionic bonding, there are no molecules. What you're left with are just independent ions that are attracted to each other. The metal becomes a positive ion, the nonmetal becomes a negative ion, the opposite charges are attracted. It's like sticking a magnet to a refrigerator. The magnet is attracted to the refrigerator, not attached to it. The smallest particle in an ionic substance is an ion. In covalent bonding, the electron clouds become fused together. They form what's called a hybrid orbital. And the electrons that they share move back and forth between those two atoms in that hybrid orbital. You can think of the hybrid orbital as a connection between the two atoms. The two atoms become attached. Ionic bonding will always result in the formation of a compound because you have to have two different elements. A compound is a chemical combination of two different elements. In ionic bonding, you have a metal and a nonmetal, so you always have two different elements, so you always form a compound. The result of ionic bonding is always called an ionic compound because there's always a compound produced. There are no molecules produced, but you always form a compound. In covalent bonding, the only thing we can say is the end result is always a molecule. You'll always share electrons. You'll always have this attachment between the two atoms. You'll always form a molecule. But you can't say that you always form a compound because these molecules can be formed when two atoms of the same element bond together. In covalent bonding, you have to have two different elements to make a compound. You got to look for that. Water is an example of a covalent molecule, a covalent bond that results in a compound. We're making a molecule here. That molecule is composed of two hydrogen and one oxygen, but more importantly, it's composed of two different elements, hydrogen and oxygen. And that's what makes this covalent substance a compound. F2 is a molecule. You have two fluorine atoms bonded together, but because it's two fluorine atoms, you cannot say that it is a compound. So again, the end result in ionic bonding is always a compound. there are no molecules there, it never makes a molecule, but it always makes a compound. That's because you need a metal and a nonmetal. By its very nature, you need two different elements. The result of covalent bonding is always a molecule because you'll always have that hybrid orbital. You'll always have that connection between the two atoms, but it's not always a compound. In order for it to be a compound, there have to be two different elements there. There are 7 diatomic elements. There are 7 times that a molecule is formed, but it is not a compound. This is whenever 2 hydrogens, 2 nitrogens, 2 oxygens, 2 fluorines, chlorines, bromines, or iodines bond together. H2, N2, O2, F2, Cl2, Br2, and I2. These are the diatomic elements. They happen because these elements are so reactive, they'll bond with themselves if there's nothing else for them to bond with. The modeling is different in ionic and covalent substances. In ionic substances, we're always going to do dots and arrows. So for sodium and chlorine, it doesn't want to do what I want it to do. I'm going to have to do it with the mouse. So this is going to be kind of messy. So sodium and chlorine, you have sodium. Sodium has 1 valence electron. You have chlorine. Chlorine has 7 valence electrons. So it looks like this. We have a metal and a nonmetal, so this is ionic bonding. My sodium has low ionization energy, low electron affinity, so it wants to lose electrons. My chlorine has high ionization energy, high electron affinity, so it wants to take them. So that's what happens. The chlorine takes the electron away from the sodium. The electron moves from the metal to the nonmetal. It's a one-way arrow because once that electron has moved, it's not coming back. The chlorine doesn't want to give it back. The sodium doesn't want to take it back. Again, this is ionic bonding. This is how we do it. Dots and arrows. In covalent bonding, it's a bit different because we're not going to transfer electrons. Both elements have high ionization energy, both have high electron affinity, so nothing wants to lose electrons, they both want to take them. To model that sharing, we have to do things a little differently. So we have 2 elements in our substance here. We have hydrogen. Hydrogen's in group 1 has 1 valence electron. We have oxygen. Oxygen's in group 16, so it has 6 valence electrons. To model it, first thing we wanted to do is determine valence, how many bonds each of these things needs to make. And the number of bonds it makes is going to be equal to the number of single dots it has in its Lewis dot diagram. Hydrogen has 1 dot in its Lewis dot diagram. It only needs to make 1 bond. Its valence is 1. Oxygen has 2 single dots in its Lewis dot diagram. Oxygen has to make 2 bonds, so oxygen's valence is 2. Now, why is this important? The one with the higher valence is the first thing you draw when you do your model. It's going to end up being the center atom that everything else is attached to. So when we model this bonding, we start with the oxygen because the oxygen has the higher valence. It has the 2 single dots. It has to make 2 bonds. So it's the center one that the 2 hydrogens are going to be attached to. So we draw those hydrogens near those single dots in the oxygens. Like so. And we draw a circle around those 2 dots to imply that they are going to be shared. So this hydrogen over here is going to share its 1 electron with the oxygen. Oxygen is going to share this 1 electron with the hydrogen. So that in the end, this hydrogen has the 2 electrons it needs to be stable. Again, this hydrogen is going to share its 1 electron with the oxygen. Oxygen is going to share that 1 electron with the hydrogen. So again, this hydrogen gets the 2 electrons it needs to be stable. The oxygen is also stabilized in the process if we count all the dots around it. 1, 2, 3, 4, 5, 6, 7, 8. It will have the 8 electrons it needs as well. So when you're doing the modeling on our practice sheet here, for your ionic one, you're going to do the dots and arrows. For our covalent one, you're going to be circling single electrons. This gets us into single, double, and triple bonding. Each pair of electrons that is shared between the two atoms represents a covalent bond. If we circle a single pair of electrons, we call that a single bond. If we circle 2 or more pairs, we'll have multiple bonds. So we circle 2 pairs, it's a double bond. 3 pairs, it's a triple bond. So in carbon dioxide, when we model that one, the center atom is the carbon because its valence is 4. It has 4 single dots around it. The 2 oxygens will attach to it, 1 on each side. So we'll have 1 oxygen over here. Again, with its 2 single dots. We'll pair up this single dot with this single. We'll pair up this single dot with that single. Leaves us 2 more places to make bonds on this carbon atom. So we'll put the other oxygen over here. And again, I apologize. It's not letting me write on the screen again. While I'm screencastifying at least. So this is a little bit sloppy. I draw this oxygen a little bit different because we're going to bond with carbons atoms that are on the bottom side this time. So I move my single dots to the bottom just to make these circles easier to draw. You don't have to do that. But again, if we look at each carbon-oxygen pairing, if we look at this carbon-oxygen pairing over here, we've got 2 sets of electrons we circled between them. That's a double bond between those 2 atoms. If we look at this carbon-oxygen pairing over here, again, we've circled 2 pairs of electrons between them. That's a double bond on the other side as well. We can go up to triple bonds whenever we do this bonding thing. We see that in HCN. Again, carbon is our center atom because carbon has the largest number of single dots. It's got 4, so it's got a valence of 4. Hydrogen only has a valence of 1. It has 1 single dot. Only needs to make 1 bond. Nitrogen has 3 single dots and 1 pair with its 5 valence electrons. I put the pair opposite the carbon this time because I need to use these 3 single dots in the bonding process. Again, this is meant to be review, not the actual instruction and teaching. I have posted other videos to Google Classroom that have the actual detailed looks at these in them. Go watch those if you need to. If we look at the carbon-nitrogen bonds, I have circled 3 sets of electrons between them. That's a triple bond. We have a single bond over here between the carbon and hydrogen. We have a triple bond between the carbon and the nitrogen. 3 pairs of electrons means you got a triple bond. There are some differences in single, double, and triple bonds, and this is the information that you have to use to answer the next set of questions. Bond length is one of the things we're talking about. Single bonds have the longest bond length, while triple bonds are the shortest. Bond energy is the other thing that's involved here, is the amount of energy stored in the bond. Is the strength of the bond. Generally speaking, triple bonds are the strongest. They have the highest bond energy. Single bonds are the weakest. They have the lowest bond energies. Double bonds are always somewhere in the middle. And again, this is the information that you're going to be using as you work through the bond strength stuff right here. A little out of order on the practice sheet, but it's there. You got it. Go for it. Properties can be different in your ionic and covalent substances because you have ions in your ionic substances. You have strong forces of attraction between the particles. We don't have permanent charges. We don't have ions in our covalent substances. So the force of attraction that holds them together is much weaker. It's either going to be polar substances with their weak positive and negative charges, or there'll be no forces at all if it's nonpolar. So we're going to see some very different properties here. Your ionic substances tend to be hard, have high melting and boiling points. They're solids at room temperature. They'll conduct electricity when dissolved. Again, that's because of their strong forces of attraction. Your covalent substances, because the forces of attraction are weak or non-existent, their properties are completely different. They're going to be soft. They're going to have low melting and boiling points. They're going to be liquids or gases at room temperature. And because there are no charges, they don't conduct electricity in any state. So the properties of our ionic and covalent substances are completely opposite. This is the lab that we did. And this is the information that you need to fill in that table right there. Next up are the types of formulas that we use for each one. In our ionic substances, we use things called imperial formulas. Imperial formulas are ratios. They don't tell us the actual numbers of anything. They just tell us the ratio of elements that are in that particular compound. In our covalent substances, we use molecular formulas. We actually describe the molecules, the number of atoms of each element that you find in the molecule. So again, for the ionic ones, it's an empirical formula because all we care about is the ratio. NaCl, for example, that's just the ratio that you have in that particular substance. It's 1 sodium for every 1 chlorine. In water, we use a molecular formula because it's covalent, H2O. It tells us there are specifically 2 hydrogens and 1 oxygen in each molecule. We do not reduce molecular formulas because we want to know the actual numbers. And this is actually not part of what you need to know for that particular section. So again, that's what you need to know to fill out that section right there. Molecular shapes, that's where we did the table and stuff and talked about the number of atoms we need, Vespert, valence shell, electron pair repulsion theory. Tells us whenever we have a 2-atom molecule, it's going to be linear. Bond angle is going to be 180 degrees. 3-atom molecules depend on if you have unshared electrons on the center atom. This is a 3-atom molecule, 2 oxygens, 1 carbon. But if you look at the carbon in the middle, there's no pairs of dots around there. That's the no unshared electron part. This one has no unshared electrons. So it ends up being linear. If you have unshared electrons, like we see right here in the oxygen, it ends up deforming the molecule into bent shape. Again, this is not meant to be a review of this stuff. I have posted a video online with the actual shapes in them. For honest, probably the biggest thing that would help you with this is that table that I gave you. This table right here. That's probably the best thing to look at when you're figuring out this Vespert stuff. In fact, it's the table that you need to fill in the missing parts of this table here. Pretty easy stuff right there. And then from there, of course, you're going to draw the shapes. And like I said, this is not meant to be a review of the actual shape stuff. This is not meant to be a review of Vespert. There's another video posted on Google Classroom that would be better suited for that. So go watch it if you need help with the actual drawing of the shapes. Polarity was next. We talked about electronegativity and how it's all about the electronegativity differences. If you're between 0 and 0.4, your bond is nonpolar and the electrons are shared equally. So bromine and chlorine. Bromine is a 2.8, chlorine is a 3.0. The difference is 0.2. That falls in that 0 to 0.4 range. Those are not polar bonds. If the difference falls between 0.5 and 1.9, then you end up with a polar bond. The electrons will not be shared equally, like hydrogen and chlorine. If we go back to this little table here, hydrogen is a 2.1, chlorine is a 3.0. The difference there is 0.9. So that's in that 0.5 to 1.9 range. They won't share the electrons equally. The electron spends more time around the chlorine than it does the hydrogen. So the chlorine spends most of its time being negative. The hydrogen spends most of its time being positive. We get some weak charges here. That's what polarity and bonds are all about. So as you're doing this part here, just look up the electronegativities. Subtract the two. If the difference is between 0 and 0.4, then you say it's a nonpolar covalent bond. If the difference is between 0.5 and 1.9, then you say it's a polar covalent bond. Pretty simple stuff there. To do the actual shapes, you have to look at the separation of charge. You have to draw the structural formula. You have to look for separation of charge. If you can separate the charge, then you can say it's a polar molecule. If you can't separate the charges, then you say it's nonpolar. The element with the lower electronegativity ends up being positive. The element with the higher electronegativity ends up being negative. So here's water. That's what the model of the bonding looks like. This is what the structural formula looks like. This is a polar bond. The difference is between 0.5 and 1.9. Oxygen, because of its higher electronegativity, is negative. Hydrogen, because of its lower electronegativity, is positive. Is right across the middle. I can draw a line. I can separate the charge, so that makes that a polar molecule. On this carbon dioxide one, that's the model. That's the structural formula. The bonds are polar. Oxygen is negative, carbon is positive. I cannot draw a straight line between that, so I don't have separation of charge. So even though it has polar bonds, it is not a polar molecule. Again, I'm rushing through this because this is not meant to be a review. This is just to help you look at the right parts of your notes, the right things to answer these questions. Ends with nomenclature. Again, the covalent nomenclature is different. We use prefixes, mono, di, tri, tetra, penta, and so on. We're going to attach those prefixes to the name of each element. We're going to change the second element's ending to IDE. Again, not trying to make this a review. I'm posting a video on covalent nomenclature for you to look at. But again, that's the thing. Hydrogen's weird. You name it like an ionic substance. So there's the bell. You're heading my way now, so I'm going to have to stop this video. Like I said, I will post a video for the covalent nomenclature. All I'm really trying to do here is point you in the right direction, where to look, what to think about as you answer these questions on this review sheet. Is it a useful video? I don't know, but since I'm out getting windows installed in my house, it's something, right? You can watch the other videos for more detailed information.